Hello everyone, welcome back to a new video. Today I'm going to be solving just a bunch of statistics questions for A-level mathematics. I am planning to do a part 2 on this, by the way. Just for now, I'm just going to solve a bunch of questions. I'm also going to be using the TI-84 from the site. I will also explain what TI Inspire users have to do, but I'm going to be using this TI-84 for our calculations. So let us begin. So our first question is that a random variable w has Poisson distribution with mean 15. So our w is distributed with Poisson 15, and it asks us the standard deviation of w. The standard deviation is going to be equal to the square root of the variance, and the variance here is 15. So sigma here is root 15. So our answer is root 15. Now here it says it is given that the probability that w is less than or equal to some value a is greater than 0.9. Now this right here is simply the Poisson CDF function, and what we have to do is we're gonna have to test all the possible values. We're just gonna have to write down a bunch of values in our TI-84. So let us begin. So we can go to the distributions and go to Poisson. Poisson is located at here, Poisson CDF. It's also the E and D keys. So that would be here and here. So we have to look at Poisson CDF with mu 15, x value, and here our x value, we're just going to test a couple of values for now. For example, let's test 15. This is, as you can see, 0.56. So we're gonna need to go a bit bigger. So let's test something a bit bigger. In this case, maybe not 15, but say 20. So this is 0.917. That is in fact greater than 0.9, but let's see if 19 also holds that. So let's see. There we go. So let's see, that's 19, and that's actually less than 0.9. So our answer here is that a is in fact 20, because that would be the smallest possible value. So here we have to write that Poisson, the probability that w is less than 19 is equal to 0.875. And the probability that w is less than or equal to 20 is equal to 0.91. What was that equal to? 917. So 3 significant figures. So we can say that the smallest possible value of a is equal to 20. This is where the 2 marks in this question come from. So we have to be careful with which values we specify. Now here it asks us the reverse question. Here now it's asking the probability that w is greater than b. So now let's think about it. The probability that the value is greater than b, that would be b plus 1, b plus 2, and on and on. So that would be the probability that w is greater than b is simply 1 minus the probability of 1 to b, which is the probability that w is less than or equal to b. So we're just gonna have to test some values again. So let us let's say 1 minus the Poisson CDF of let's test 19 again. Let's see if that's too high or too low. That's 0.124. That is way bigger than 0.01. So what we have to do is we're gonna have to check a lesser value. So let us say 1 minus. Or we are gonna have to check a bigger value, pardon. 1 minus the distribution Poisson, let's say 25 maybe. That's 0.006, which is way too small. So let us test like 20 maybe, 22. Hold on, hold on. Let us test. Maybe 22. That's 0.03. That's too big. So let's test 23. This is getting a bit annoying, but hey. Let's test 23. Okay. And that's still too big, so let us test. Let us test 24. It's still too big, so we can see that it's between 24 and 25. So we saw that for B, the probability that W is greater than 24 is equal to 0.0111. 0.011, is it 111? Is it? It's 112. So 3 significant figures, and the probability that W is greater than 25 is equal to. Let's see. It's equal to 0.00618. 0.00618. So this is less than. This is greater than 0.01. This is less than 0.01. Hence, we can say that our smallest possible value for B is 25. All right, let us continue with the next question. So here we are. Here it tells us that X is distributed with a Poisson distribution with mean 3, and it asks us the probability that X is less than or equal to 3, or is bigger than or equal to 3 and less than 5. So this is essentially meaning the probability that X is equal to 3 and 4, and the sum of these. So for TI inspired users, this is just the Poisson CDF with lower bound 3 and upper bound 4. For 84 users, what we're going to do is we're going to calculate the probability that X is less than or equal to 4, and we're going to subtract the probability that X is less than or equal to 2. So we calculated all the sum. So we calculated all the sum up to 4, and we are subtracting the sums up to 2 from that. So that will be, let's see, that will be the Poisson CDF. So that will be the Poisson CDF, this time with mean 3. And X value 4 and minus Poisson CDF with mean 3 and X value 2. So that will be 0.392. So 3 significant figures, because that's what it asks us for. So we can just write 0.902. All right. Now it says here that the random variable t is binomially distributed with n equal to 5 and 0.02 probability. And it asks us that why this can be approximated with a Poisson distribution. So here the n value is large and the p value is small. Hence we can approximate it with a Poisson distribution. And our value of lambda right here, is going to be equal to n times p, which is 500 multiplied by 0.02. That would be 10, I think. Yeah, that would be equal to 10. So our value is 10. Right now, let us solve this question. So here we have our value of c to be defined as the sum of the three variables that we've worked with so far, and it is said that they are independent. So here c is going to be also modeled by a Poisson distribution, since all three of these variables are independent and distributed by Poisson. So its mean value is going to be the sum of all the mean values. So w's mean value was 15, x's mean value was 3, and y's mean value is 10. So that's going to be Poisson of 28. And it asks us to calculate the probability that c is less than 3. So that's going to be equal to the probability that c is equal to 0 plus the probability that c is equal to 1 plus the probability that c is equal to 2. Now remember, the probability that c is equal to some value x here, in this case, is going to be the formula for this. It's going to be e to the negative lambda, so e to the negative 28, multiplied by lambda to the x, so 28 to the x, divided by x factorial. So I'm just going to write this, and I'm going to factor out all the e to the 28 here. So it's going to be e to the 28 times 28 to the 0 divided by 0 factorial. That's 1 divided by 1, so it's 1. And then we have 28 divided by 1 factorial, so that's just 28. And then we have 28 squared divided by 2 factorial, or just 2. You can quickly put this into RTI for calculation. So that's going to be 1 plus 28 plus 28 squared divided by 2. That's 421. So our answer is going to be 421 times e to the negative 28. Now let's solve this question. I'm not going to solve the other part of this question. That's for later. It says us the time taken for a company, for the bus time of a company, or the bus travel time for between two towns is modeled by a normal distribution. So I'm going to call that variable x, and it's going to be distributed normally with mean 38 and standard deviation 11, so variance 11 squared. And it asks us to find the probability that the time taken for a bus travel is more than 50 minutes. So we can just quickly plot that into RTI. This time it's going to be the normal distribution. So it's going to be the normal CDF distribution. Here we are asked to find the probability that x is greater than 50. So for the lower bound, we can write 50. For the upper bound, we're just going to write a big number, so like 1 bajillion. For the mean, we can write 38. And for the sigma value, we can write 11. That's going to be 0.13765. So it asks us to find for three significant figures. So it's going to be 0.13, it's not 7, but 8. All right, now let us continue with this question. This is a hypothesis test question, which is pretty important. As you can see, it's 7 marks, so we have a lot to do. Now let's begin. So here, Sam has a 90% success rate for repairing damaged mobile phones. And this tells us that this is probably going to be a binomial distribution question. So according to him, he claims that he has improved his success rate from 90% to something higher. And here we're gonna be having an n value of 50, and our test value is gonna be 49. And it asks us to do this with 1% level of significance. All right, let's begin. First of all, here, let's define our p-value. P-value is the success rate. Success is written with 2 S's. Success rate for repairing the damaged mobile phones. Now let us present our null hypothesis. Remember that the null hypothesis is always going to be like the devil's advocate. It always is going to be the one that's suggesting that nothing has changed and that it's going to be the opposite of this claim pretty much. So our H0 is going to be that of P is equal to 90%, so 0.9. And here our alternative hypothesis, or H1, is going to be basically it's going to be the claim made by Sam in this case. So he's claiming that the probability value has increased, so P is greater than 0.9. And now let's think. This right here indicates it's a one-tailed test, and specifically an upper-tailed one-tailed test. So if we draw the number line in which the values our binomial distribution can take, we can see that the critical region is going to be somewhere in this like upper end, and we're going to have to find if our x value lies within this critical region, or if it lies in the acceptance region. Now here we can continue on by assuming H0 in hypothesis test. In hypothesis test, we always assume H0 to be true and try to reject or fail to reject H0 in the end. Assuming H0, we can say that our random variable x, so our test statistic, in this case the number of phones he has repaired, is binomially distributed with n value of 50 and probability p, so assuming H0, that's 0.9. And now, given a test value x, we need to find that the probability that our test statistics is greater than or equal to x. And notice how this, if that's greater than 0. In this case 0.01, and that means it lies outside of this range, since the sum of the total binomial probabilities after and add it is going to be greater than 0.01. If it is less than 0.01, then it's going to be in the critical region. So let's test this. So here it's going to be the probability that our test statistics x is going to be greater than or equal to our test value, which is 49. So that's going to be simply the probability. That's going to be simply the 1 minus. So this is going to be 49 to 50. It asks us these two values. So that's simply the probability that 1 minus the probability that x is less than or equal to 48. So we can quickly plot that into our TI-84. Of course, for Inspire users, you can just say the lower bound is 49 and the upper bound is 50. It's not that difficult. So I just write 1 minus the binomial distribution. The binomial distribution is binomial CDF. The binomial CDF is B. This is the number of trials of 50, the probability value 0.9, and x value 48 in this case. So that gives us 0.03378. So I'm going to write the three significant figures. That would be 0.0338. 0.0338. Now we can see that that is in fact that is in fact bigger than 0.01. That's bigger than 0.01. What this means is that if it's bigger than 0.01, that it lies in the acceptance region. So if it lies in the acceptance region, we have to accept H0. So hence, and by accept I mean we fail to reject H0, or we don't reject H0. You can't say we accept H0, we have to reject or to not reject H0. And the final step for our hypothesis test is to relate this conclusion of the test with the context of the problem. So here here we fail to reject H0. That means there isn't sufficient evidence to suggest that the probability is greater than 0.9. There isn't sufficient evidence to support Sam's claim. So we have to write that, meaning there isn't sufficient evidence of course, we always have to say there isn't sufficient evidence in this case. Evidence to suggest Sam's claim. What's Sam's claim? Sam claims that using the gel has improved his success rate. So that's his success rate. Success is again written by two S's. Has improved by using the gel. If we were to land in the critical region, so if this value were to be less than 0.01, we would have to reject H0, meaning that there would be evidence suggesting that the probability this probability is greater than 0.9. Hence, we would have evidence to suggest that his success rate has improved. All right. Right, now let's continue with this question. These are simpler questions, only with 1 mark. So here it asks us what is meant by a type 1 error in the context of the hypothesis test. So if you remember, a type 1 error is when we reject the null hypothesis, even if it's when we erroneously reject the null hypothesis. So it happens when we reject H0, but H0 is actually true. Of course, that's not going to be what we write in our answer, because here it asks us to explain what is meant by the type 1 error in the context of the hypothesis test. This is really important. You will lose marks if you don't explain what it means in the context, and pretty much all of these types of questions are asked within the context of the question. So here in the context, H0 would be that his success rate hasn't changed, and H1 would be that his success rate would have increased. So rejecting H0 is equivalent to saying that his success rate has increased. So it would be so type 1 error would occur when if we supported Sam's claim of the success rate improving when it actually has not improved. Hasn't improved. Right, now it asks us that a situation is given, so that all the mobile phones owned by a family are damaged in a household flood, and all of these are sent to Sam. And it asks us why a binomial distribution is not likely. And this is because, well, here the event of these phones getting damaged are not independent from each other. They all happen together, and hence one of them happening is completely dependent on the other happening. Hence we can say that the event of the phones getting damaged, and in this case, the events of the phones getting damaged in this case are not independent, and hence a binomial distribution would not be. A binomial distribution is not a good model for this, because in a binomial distribution all the events have to be an event occurring has to be independent from another event, another probability succeeding. Not a good model. Okay, so let's now continue with this question. Here it gives us a general normal distribution with any given mean and standard deviation, like this. and it asks us to find. So it asks us to find the value of A. If it's this region is symmetric by the mean, it has a probability of 95%. Now, here it doesn't actually matter what distribution you choose. You can just choose any random distribution and calculate the values with accordance to that. But for simplicity, I'm just going to choose the value of mu to be 0 and the standard deviation to be 1. In this case, x is distributed with the simple z distribution. And in the case for the TI-84, this is we just simply need to find the inverse norm of 0.95 with the mean 0 and the sigma value 1 from the center, because that's exactly what this gives. So let's quickly do that. So we have to choose the inverse norm, this function right here, with area of 0.95 and sigma 1, mu 0 and sigma 1, and here it's going to be center tailed. So let's just quickly find that, and as you can see, it gives us the two values for this. So our A value here is going to be 1.9599363, whatever. So it asks us to find the coefficient of sigma, which is A. Oh no, hold on. It asks us to find what A is in terms of sigma, yeah, pretty much. So in this case, that would be, so here our mean was 0, so this value is going to be this 1.995 sigma, or times 1, but for any given sigma it would be 1.995 times sigma. So A in this case is going to be this value, 1.9599. 1.9599, I think that's the coefficient of sigma. It asks us for 4 decimal places, 9599. Oh, okay, then if that's the case, then well, we have to round up because there's a 6 here. So we have to round up. That would mean 1.956. So would be 1.9600 is the coefficient of sigma. Now, for the TI Inspire, I believe there isn't a center tail or a left or right tail for the inverse norm, and the TI Inspire is for TI Inspire users, you have to do it with a left tail. So to do that, you would have to divide this section by 2. So that would be to divide 95%, so 0.95 over 2. That would be 0.475. So this area would be 0.475. So this area right here would be 0.5 minus that. So 0.5 minus, wrong. Oh god, what did I do? 0.5 minus this value, that would be 0.025. So this value would be this area would be 0.025, and then you would have to find the inverse norm of that. So let's go to distribution, and the inverse norm of that, 0.025. Of course, for the TI Inspire it would be left, and that would in fact give you the exact same value as here. Right, now let's continue with this question. It asks us that there's some value B and that this area is 16%. Now again, this is a simple inverse norm question, so we can assume a z distribution again. So let's find the inverse norm. Oh, that's the wrong menu. Inverse norm of 0.06 or 0.16, this time with from the right. So that would be 0.94457. So what this means is that this value, this length right here is of 0.94 or whatever sigma. So we can write B as this mu plus 0 point whatever coefficient times sigma. Now it asks us to find the coefficient of sigma to 4 decimal places. So here we can write b as mu plus, let's see, 4 decimal places, that would be 0.9445. So 0.945. 0.9945. 0.9945 sigmas. That will be our answer. Now here it asks us to sketch the total region represented by this weird expression right here, where c is a positive constant. Okay. So this type of inequality is a weird inequality. Basically, what it's telling us, if we take like the square root of both sides, is that x minus mu's absolute value is greater than c. And here c is positive, so we don't need to take the absolute value. Now what this means is, here it's mu, here will be mu, and the x minus the mu value, so x's distance from mu is greater than c. So here will be mu minus c, here will be mu minus plus c. And this is the region beyond this area. So that would be mu plus c in this case here. So, and that would, so, and then symmetrically, like this, there would be mu minus c. And this region is labeled by, is going to be shaded in, it's going to be this region of the normal distribution. Right, now let us continue with this question. It says that the random variable y is defined with a normal distribution m, normal distribution with mu m, and variance 0.8 m. So that would mean the sigma is the square root of 0.8 m. Now it tells us that the value of y being less than 205, the probability of that is 0.97. So again, this is an inverse norm question. So here we need to find the inverse norm, or the z value of 0.975. So on the basic normal distribution, we need to find what value would this area with 0.975 would lie at. That's simply the inverse norm of 0.975. So let's quickly calculate that. The inverse norm of, from the left, of course, this time, 0.975 from the left. Let's calculate that. That would be 1.95996 something. I'm gonna be doing calculations with this, so there's no need to round this value. 95996. 996. I mean, I'm gonna write as many decimal places as I come up to. It doesn't matter. So here we can use the formula that z equals x minus mu over sigma. So in this case, z, or this value of 1.9, or actually we should, yeah. In this case, z times sigma plus mu plus equals x. So we can get an equation from this. So here our z value is 1.95996 something multiplied by our sigma, which is 0.8. So multiplied by root 0.8 multiplied by root m plus the sigma, our mean, which is m. I'm going to write that as root m squared, which is equal to x. So our x value here is 205. I'm just going to subtract that. So subtracted by 205 is equal to 0. This right here is a quadratic equation in terms of root m. Alright, so this is a quadratic equation in terms of root m, and to solve it we can use our calculator. I believe it's pretty simple to do in the Inspire. I think there's a, you just open the functionality of you can just open the numerical solver and just write an equation. It shouldn't be that difficult. 1484 does. We're gonna have to do some stuff. So in the 84, to open math, and then we go to, where do we go to? We go to, there should be numeric, oh, there we go. Numeric solver, here we go. That's the equation solver. So this simply solves the equation E1 equals E2, yeah, there we go. So our equation in this case, let's see, that's going to be, it's a bit annoying. I'm just going to call root mx. I mean, we could write it as root m. I don't think that would cause a problem. Just going to call root mx, and that plus root 08. So that would be square root of 0.8 multiplied by the 1.959969 multiplied by x, and then minus 2.205, and that should equal 0. So there we go. Now here we have to put in a guess value for our x. This is how the TI-84 solves, numerically solves equations. And then to solve, we need to press alpha lock and then enter. There we go. That finds us the value for root m. Here root m is apparently equal to 13.46810.103. That's probably enough significant figures. I don't think we need more. So now we simply need to calculate the square of that. So 13.468 1033 squared is going to equal 181. It's going to be, so here m is going to 181. I think, it's just 181. Oh, it asks us for 2 decimal places, so then it's 181.38, so 39. Alright, now let us continue with this question. This seems to be a Poisson question with, it seems to be a Poisson hypothesis testing question, so let's do that. Now, the total number of breakdowns of boats by a transport company is modeled by a Poisson distribution with parameter of 4 breakdowns per week. Alright, so let's call that variable x. It's going to be distributed in Poisson, and it's going to be 4 breakdowns per week. And it asks us to find the probability that the total number of boat breakdowns in a week is 3, alright, so here that's the probability that x is equal to 3. You can quickly calculate that using RT84. You can also use the formula, but nobody cares about that, so let's quickly calculate that. That should be the distribution, and that should be Poisson CDF, so that's that, right? No, that's the wrong button. I think I pressed the wrong button. There we go. I need to press this. That's Poisson PDF with mean 3, not with mean 4, and x value 3. So that's 0.195 to 3 significant figures. 0.195. There you go. Now here's the actual question. It's 8 marks, so we have to do a lot again. These sorts of questions are important. That's why you need to learn hypothesis testing pretty well. So the total number of breakdowns of buses owned by the same transport company. So last time it was boats, now it's buses. This time this is also modeled with a Poisson distribution of this parameter 2.5 per week. And the breakdown of boats are independent of the breakdown of buses in this company to work on the boats and the buses. So here, several months later, it gives us that there has been 7 breakdowns. So this is going to be our test value. However, it's important that this is of boats and buses. So we're going to have to sum the 2 distributions. And it says during a 2-week period. So the previous, we were giving these distributions to be per week. And we're going to be needing to double that. And the company claims that the reduction, so the average value has decreased of this distribution, and we have to do a 5% test level of significance. So here we said x was distributed with Poisson 4, and I'm going to call y to be the number of breakdowns of boats per week, or breakdowns of buses per week. So this would be the Poisson of 2.5. So the total number of breakdowns and buses, or the total number of breakdowns of boats and buses per week is x plus y. That would be the Poisson of 6.5. And we need the total number of breakdowns during a 2-week period. So that would be double that. So I'm just going to call t to be the Poisson is 13. So I'm just going to let t be the total number of breakdowns of boats and buses during a 2-week period. All right, now these are the groundwork. Now let's begin with our hypothesis test. So we'll set the lambda to be the total number, or the average number of breakdowns of buses and boats in a 2-week period. So now our null hypothesis, again the devil's advocate hypothesis, is going to be completely opposing this claim given by the maintenance company. So it's just going to be saying that the lambda value is 13 and has not changed at all. The alternative hypothesis is going to be the claim given by the company here. So the company claims that there has been a reduction in the total number of breakdowns. So our value of lambda is less than 13. Now again, we can say that assuming h0, we can say that our test statistic t is modeled by Poisson of 13. Now here we're searching for lambda less than 13. This would mean we need to do a lower-tailed test, so one-tailed lower-tailed test. So if you think about the number line in which the Poisson distribution can take the values of, so the number line of t, we need to find the values in which there's going to be some critical region such that the sum of the probabilities in this region is less than 0.05, which is our level of significance. So in this case, for a given test value, test value t, the probability that our random variable t is less than that of t. If this is greater than 0.05, then we know that it lies somewhere in this region, so it's in the acceptance region. If it lies less than 0.05, we know that it lies in this region, hence it is in the critical region. So now we need to test that. So the probability that t is less than our test value. Our test value is 7. There has been 7 breakdowns of boats and buses, so it's less than or equal to 7. This is simply the Poisson CDF of 7. So let's quickly check that. That's going to be the distribution. The Poisson CDF. Our mean value was 13. X value here is 7. So let's test that. That's going to be 0.0540. This is 0.0540. And as you can see, this is indeed greater than 0.05. So it lies outside, so the sum of the probabilities until 7 is bigger than 0.05. Hence, it lies in the acceptance region, outside the critical region. If it's in the acceptance region, then we fail to reject H0. Hence, we fail to reject H0, meaning, and now we have to connect this to the context. So if we fail to reject H0, that means there isn't sufficient evidence to support the company's claim, which is H1. So there isn't sufficient evidence. Let's write that. There isn't sufficient evidence to support to claim. Oh my god! To claim that. Oh god, I can't write. Claim that the company's claim is that there has been a reduction in the total number of breakdowns of boats and buses per week. Evidence to claim that there has been a reduction in the total. Oh my god, I can't write. In the total number of breakdowns of buses and boats per week. Of course, these hypothesis test questions are very detailed, and as you can see, it is 8 marks for a reason. So you're gonna have to write. You should write it long and detailed like this. Don't miss anything over. There is no reason to anyway. All right, now let's continue with this question. This seems to be a Poisson approximation question, and then it's gonna have us carry out a binomial hypothesis test. So that's 6 marks. So that's pretty important. And then it's gonna ask us a type 1 error. And then it's gonna ask us the probability to make a type 1 error. So let's begin this question. All right. So so according to a television channel, 3% of its viewers watch the local news program at least once a month, and a random sample of 100 viewers are taken. So here I'm gonna say X to be the number of viewers that watches the program at least a month. So that's going to be by here in this run. So I'm going to say X to be the amount of viewers that will watch the channel's news in the sample of 100 people. So that's going to be binomially distributed with 100 trials and a probability value of 0.03. Now it tells us that we need to use a Poisson approximation to estimate the probability that less than 4 viewers watch the news. So we can, since the n value is large and the probability is low, we can approximate this with y, with Poisson of 100 times 0.03. So that's going to be 3. So it's Poisson 3. And it asks us to find the probability that less than 4 viewers watch the local news at a program at least once during the last month. So that would be the probability that y is less than 4, and that simply is the probability that y is less than or equal to 3, which is the Poisson CDF. So let's quickly figure that one out. That's going to be the Poisson CDF of with mean value 3. Was 3 and less than or equal to also 3. So we can just quickly find that. That's going to be 0.647, so 3 significant figures. 0.647. There you go. Now, this question is 4 marks for some reason, but it's pretty simple. Now let's get to the actual part. So here a random sample of 20 viewers is taken. So that's probably going to be our n value in the binomial distribution, and 3 of those viewers have watched the local news, so that's probably going to be our test value. So the television channel claims that the proportion of its local news has changed. So it's important. This is a sign of that we're going to be doing a two-tailed distribution, and it asks us to do a 5% level of significance test with no distributional approximations, meaning we have to do a binomial test, right? So I'm just gonna ignore this question and say that X is gonna be our random variable. So our test statistic of the number of viewers who watched the local news in the sample of 20. So that's gonna be binomial distributed with 20 and probability 0.03. Or let's just say probability P. Now here P is the probability. Let's carry out the test from now on. Here P is going to be the probability, or not the probability. It's going to be the percentage, the proportion of viewers that watch. The proportion of viewers that watch what was it called? The local use program. At least once during the last month. So now let us begin our test. So the null hypothesis is going to state that this probability value has not changed at all. So it's going to be P is going to be said that P is equal to 0.03. That was what it was before, 3%. And our alternative hypothesis, H1, is going to state that P has changed, because that is the claim of the company or the television channel, which says that it has changed. So it is not equal to 0.3 or 0.03. Now, here, let's just write that, assuming, if I can write on how the hell did you write it? Oh, assuming H0, you can state that a random variable X is binomially distributed as n20 and probability 0.03. Now, this right here, the fact that the claim is that the probability is not equal to 0.03 suggests that we're going to do a two-tailed test. So if we consider the number line in which the values of the binomial distribution or our random variable can take, so X right here, we're going to have a two-tailed distribution, like something like this, and this is going to be the acceptance region in the middle. So for a given statistic X, or a given test value X, you need to find the probability that, okay. All right, so hold on. We need to do a 5% level of significance. So the values, the sum of the values in this region have to be less than of 0.025, and in this too. So if you find our test value X, so we need to state the condition for when it's in the critical region and when it's in the acceptance region. So if our random variable X, the probability of our random variable X being less than our test value X is, if it's bigger than 0.025, or if it's less than 0.025, or if the probability that our test variable X is greater than our test value X is, in this case, also less than 0.025, we can say that X is in the critical region. I guess I don't have space, whatever. So let's test both of these. So the probability that X is less than or equal to our test value, which in this case is, what's our test value? It's 3. There you go. So let's just quickly calculate that. That will be the Poisson, not Poisson. That will be the binomial CDF. Binomial CDF with 20 trials with that's not 20. 20 trials with probability 0.03 and X value of 3. So that's really big. That's 0.997 something. Now, what this suggests is that this doesn't suggest anything. Actually, it doesn't suggest some acceptance of the critical region. It simply says that it's somewhere in here. So let's also test the other condition. So that X, the probability that X is greater than or equal to 3. This is, this is asking for 3 and 4 and so on. So this is simply going to be 1 minus the probability that X is less than or equal to 2. So I can quickly calculate that. That'll be 1 minus the binomial, the binomial CDF with 20 trials, probability 0.03, and X value 2. That will be 0.021. 0.021 of 3 significant figures, whatever. And is this less than 0.025? Okay, so this value is greater than 0.025. That doesn't tell us anything, but this value is less than 0.025. What this means is it is in fact in the critical region, so we have to reject H0. So hence we reject H0, and now we can relate it to the context of the question. So rejecting H0 simply means that this probability value, it has in fact changed. So we have enough evidence to support the television channel's claim, meaning there is evidence to claim that the proportion, there's evidence to claim that after that, we just got to write this line. So evidence to claim that the proportion of viewer, I'm not going to write all of this. Basically, you just have to copy this line. There is evidence to suggest that the proportion of the television channel's viewers that have watched the local news program at least once a month has in fact changed. All right. So now here it asks us to describe in the context of the test what a type 1 error is. Now remember what a type 1 error is. A type 1 error is to reject H0 when it is in fact a type 1 error. It's usually written as capital. Error is to reject H0 while it is true. And important thing is that this wants us what a type 1 error is in the context of the test. So to reject H0 is to claim that the claim that the television channel is right and the proportion of viewers at least once a month has changed while it has not. So a type 1 error, so you can write a type 1 error in this case would be to claim that the proportion, blah blah, I'm not going to write all of this, has changed while it actually has not. It actually has not. Now here, this is an annoying question. It asks us it tells us that another sample is taken, and from here we're gonna get another different test value x, and it asks us the probability of making a type 1 error. Now here it assumes that H0 is true. So what this means is it is asking us the probability that we reject, the probability to rejecting H0. Now, what in this case, the condition we need to reject H0 is for our test value to land somewhere in this critical region. So essentially, we need to find the total probability of of falling in this critical region. Now let's see. For that, we need to find the critical value, essentially critical values in this case. So let's say that there's two possible ways of falling into the critical region in this case. You can either fall into it from the left, which is this case. So for which we need to find for which values x is this condition satisfied, which this condition would tell us that our x is in the left critical region. So this right here is simply the Poisson CDF, or not Poisson, binomial CDF. So let's test with, for example, again, the number of trials, 20, and probably the same. Let's test with 1. That's way too big, so I'm gonna assume that we're not gonna get. And let's test it with 0, and yeah, that's 0.54. That's like something let's just write this. This is equal to 0.548 something, I don't remember. It's 548, yeah, it's 544, which is greater than 0.025, which means now, since the test value can't fall below 0, that basically means that there is in fact no left tail in this case. So we're not technically doing like a two-tail test, because the probability values are simply two. And yeah, we don't have this region in the test actually, so we simply have to look for what this region is. So that region would be found by finding the probability values of x, such that the test values x such that our test statistic being greater than or equal to x is less than 0.25. So now let's test a couple of values. This would be, by the way, this would be 1 minus the probability that x is less than or equal to x minus 1, because we're simply just removing this part. So yeah. All right, so let's test for 2. So let's test the probability that x is greater than or equal to 2. What would that be? That would be 1 minus the probability that x is less than or equal to 2, or less than or equal to 1. So what would that be? Well, we actually just already found out that's this value right here. So that would be 0.1198. 0.1198. This is in fact bigger than 0.025. You can also quickly calculate what x is, the x value to be greater than 3 is. This is going to be, let's see, that's going to be 1 minus the binomial probability, binomial distribution. So that's Poisson. Oh god, what am I doing? There we go. Binomial CDF, that's P trials 20 and P 0.03, and x value of 2. So that's 0.0210. All right. That's 0.0210. This is indeed less than 0.025, which basically tells us that this is where our critical region is. So if we consider the values, so 2 and 3 and 4, so the sum from this part is bigger than 0.025, but the sum from this part is less than 0.025. So our critical region would be from 3 and onwards. So we were trying to find the probability of landing on the critical region. So that would be the probability of getting a 3 and further, which basically is the probability of that our test statistic is greater than or equal to 3. So that's exactly this value right here. So our answer is 0.0210 to 3 significant figures. All right, everyone. Now let's solve another similar question. If you didn't get it, this is going to be the final question for the day. So let's solve it. I guess it's similar to the last question. It's going to be a Poisson hypothesis test question, I think. Yeah, it's a Poisson hypothesis test. All right. So let's begin. Emily counts the number of cars X going past her house during a 10-minute interval. And Emily believes that X is modeled by a Poisson distribution with mean 6.5. And it asks us the probability that X is equal to 4. That's super simple. Let's do it quickly. That will be the Poisson. That will be the Poisson PDF. Which was that? That was this, right? Poisson PDF. Yeah, there we go. So Poisson PDF, that means 6.5 and X value of 4. That is 0.1118. So it doesn't ask us anything. It's gonna be 0.111. It's gonna be 0.112. There we go. So that's 0.112. Super simple. Emily also counts the number of lorries going past our Astringer 10-minute interval. So here, Emily believes that the distribution of y can be modeled as a Poisson of 0.5. Now assume x and y are independent. From this, it asks us to find the probability that total number of cars and lorries. So the total number of cars and lorries would be x plus y, which is distributed with the Poisson distribution of 0.5 plus 6.5. And that would be, what would that be? So, and then it is asking us the probability that the total number of cars and lorries in 10 minutes is less than 3. So it's going to be asking us that this is less than 3. That is basically the probability that x plus y is less than or equal to 2. So let's quickly find that. What would that be? That would be the Poisson distribution. God, I'm so tired, don't I? That would be the Poisson PDF or CDF of its mean 7 and x value 2. So that's 0.0296. That's for those 3 significant figures. 0.0296. There we go. Right, that's not too important. Okay, here we go. After a factory is built nearby, the 3 lorries go past Emily's house in 10 minutes. So I'm assuming this 3 right here is going to be our test value. And Emily claims the mean of y has increased. All right, so here we're going to be doing a Poisson distribution with our value of y, which is Poisson distributed with Poisson of, let's just call it lambda, where lambda is the number, the total number of lorries that go past Emily's house during a 10-minute interval. So that's the total number of lorries that go past. Oh God, that can go past Emily's house in 10 minutes. All right, now let us state our hypotheses. So the null hypothesis is going to be that of the lambda value has not changed at all. So that the lambda value was 0.5. So let's just call it that. And the alternative hypothesis is going to be Emily's claim, which claims that lambda has increased. So lambda is greater than 0.5. And we assuming H0, we can state that the probability, we can state that y is modeled by a Poisson distribution with mean 0.5. All right, now the fact that we are trying to find, the claim is that lambda is greater than 0.5, we need to do a upper tail test. So if we consider the values that our Poisson variable can take, so values of y, we need to find the critical region somewhere in here, such that any given x such that the probability after this point is less than our significance level, which is 0.05. So what would that be? So if some random, if our test value y, if we need to calculate the probability that our test statistic is greater than or equal to y, our test value, that has to be less than 0.05, or that if that's less than 0.05, that means it has landed in the critical region. All right. So let's quickly test that. So we need to find the probability that y, our test statistic, is greater than or equal to our test value, which is 3. That is 1 minus the probability that y is less than or equal to 2, because it's going to be 3, 4, and onwards, so we have to subtract the first 2. And that would be, let's quickly calculate it, that would be the 1 minus the Poisson CDF with mean 0.5 and X value of 2. So that's 0.01438. So that's 0.01. Wait, what was that? 0.01438. There we go. Just let me clean this up. There we go. So this 0.01438 is in fact less than 0.05. What this means is that it is in the critical region. So we fail to we reject H0 because it is in the critical region. So hence we reject H0, meaning there is evidence to support. There is evidence to support Emily's claim. So what is Emily's claim? So there is evidence to claim that the mean y has increased. So there is evidence to claim that the total number of blah blah blah, as you can write it. I'm assuming you probably wouldn't have a problem if you just wrote this as well. The total number of lorries that go past Emily's house in 10 minutes has increased. Right, that is our hypothesis test. Now the next question again is the exact same question as before. It explains in the context of the test what the meaning of a type 1 error is. So a type 1 error, again, is to reject H0 when it is true. So in this case, rejecting H0, so supporting Emily's claim. So in this case, the claiming the mean y, I guess the total number of lorries, blah blah blah. You can write that. I'm not writing all of that. The total number of lorries that go past in a 10-minute interval has increased, while it actually has not. So again, it asks us the probability of making a type 1 error in the test. This again isn't too difficult. To make a type 1 error, we have to reject H0, assuming of course H0 is true. So to reject H0, we need to land in this critical region. So basically we need to we have to find the critical region. So we need to find a probability that we reject H0. So that's the probability of landing in the critical region. So a given test value y. Now we can so we need the test value y such that the probability of our test statistic y being greater than or equal to our value y is less than 0.05. So this is the 1 minus the probability that y is less than y, so y is less than or equal to y minus 1. So let's calculate a couple values for that. So let's see, let's test like 3. Maybe that will be good. Oh, actually, we have to do 1 minus. That will be 1 minus the Poisson CDF. Again, with mean 0.05. Let's test. Let's test 2, which would be, let's test 3. I guess to test I can't talk. to test 3, we would have to have x value 2. There you go. So that's 0.0143. So the probability that y is greater than 3 is 0.0143. I guess it's more significant, whatever, I don't care. I guess I can write 9 for now, what doesn't matter. So this is indeed less than 0.05. So this is in fact in the critical region. Let's test 2 as well, because we need to find where the boundary is. Maybe 2 also fits. So that would be 1 minus the Poisson CDF. The Poisson CDF is mean 0.2 and x 1. There we go. That would be 0.0902. 0.0902 or whatever. Again, doesn't matter. There we go. And that is indeed not less than 0.05. So this is not in the critical region. So we can say that our critical region begins with 2. So it begins with 3. So it's from 3 and onwards. So now we need the probability to land on this critical region, which would be, well, the probability to be greater than or equal to 3, which is 0.0144. And 3 significant figures. And there we go. That will be it for today. Thank you. Thank you for listening, everyone. I hope you learned statistics well. It's a really boring topic. I'm so tired. Oh my god. All right. Anyway, bye. I'm gonna make another statistic video about the other topics that I'm not covered in this video, such as like probability density functions and continuous random variables and all that, and like sampling normal distributions and other hypothesis tests probably, but that's for later. Anyway, thanks for listening.